What if the universe operates by rules we can't yet see? Rules so subtle, so deeply woven into the fabric of reality, that we've only begun to scratch the surface of their existence. Think about this for a moment. Dark matter, that mysterious substance that refuses to interact with light, makes up roughly 27% of the universe. And yet we can't see it, touch it, or even fully understand it. It's like an invisible hand guiding the cosmos, pulling strings behind the scenes. That's just one of the hidden rules of the universe, a puzzle waiting to be solved. But what else is out there? What other laws govern the way galaxies spin, particles behave, or even time itself flows? This isn't just about science, it's about the very nature of reality. Uncovering these hidden rules could change everything. Imagine a world where we finally understand why quantum particles can be in two places at once, or why gravity seems to play by different rules on cosmic scales. These aren't just abstract ideas, they're clues to a deeper truth, one that could reshape technology, philosophy, and even the way we see ourselves in the grand scheme of things. The universe is whispering its secrets, and today we're going to listen. So let's embark on a journey together, one where we'll explore the strange, the unexplained, and the downright mind-bending. From the eerie behavior of black holes to the bizarre dance of entangled particles, we'll dive into the mysteries that scientists are still struggling to unravel. This isn't just a video, it's an adventure into the unknown, a chance to question everything you thought you knew, because the universe is far stranger, far more mysterious than we've ever imagined. And the best part, you're about to discover why. Time feels like the most reliable constant in our lives, ticking forward at the same steady pace, never speeding up or slowing down. But what if that's just an illusion? Einstein shattered this idea over a century ago when he revealed that time isn't rigid at all. It bends, stretches, and warps depending on where you are and how fast you're moving. Near a black hole where gravity is unimaginably strong, time crawls so slowly that an hour there could mean years passing elsewhere. Even here on Earth, atomic clocks flown on planes at high speeds tick measurably slower than those on the ground. This isn't science fiction, it's the universe showing us that time is far more fluid than we ever imagined. So, is time even real, or is it just a human invention? Physicist Carlo Rovelli suggests something radical, that time might not exist at all in the fundamental laws of physics. At the quantum level, where particles flicker in and out of existence, events don't always follow a neat sequence. Cause and effect can blur, and the idea of past, present, and future starts to unravel. If Rovelli's right, then everything we experience, the flow of seconds, the aging of stars, the march of history, might just be a trick of perspective, like watching a river and mistaking its currents for something solid. But if time is an illusion, what does that mean for space? The two are deeply intertwined, forming the fabric of reality itself. And if time can bend, then space holds secrets even stranger, warped dimensions, hidden portals, and forces we've yet to name. The deeper we look, the clearer it becomes. The universe plays by rules we're only beginning to glimpse. Einstein called it spooky action at a distance, a phenomenon so bizarre that even he struggled to accept it. Quantum entanglement, where two particles become mysteriously linked across any distance, instantly mirroring each other's states no matter how far apart they are. Picture tossing a pair of gloves into opposite ends of the galaxy. If you find one is left-handed, the other immediately becomes right-handed, faster than light could ever travel between them. This isn't hypothetical. The 2022 Nobel Prize in Physics was awarded for groundbreaking experiments proving this strange connection is real. defying everything we thought we knew about space and time. What's truly mind-blowing is that this spooky action happens instantaneously, as if the particles share some hidden line of communication that bypasses the universe's speed limit. Scientists call this non-locality, a clue that there might be a deeper layer of reality where separation is just an illusion. Imagine every atom, every star, every living thing subtly intertwined in an invisible web, reacting to each other in ways we can't yet perceive. Could this be the universe's way of hinting that everything is fundamentally connected? The implications are staggering. If particles can influence each other across cosmic distances, what does that mean for cause and effect, for the very nature of distance itself? Some theories suggest that entanglement might be evidence of higher dimensions or a holographic universe, where what we see as vast emptiness is actually packed with hidden threads of information. Others wonder if this phenomenon could one day revolutionize technology, enabling unhackable quantum networks or computers that solve problems in seconds which would take conventional machines millennia. But here's the real mystery: why does the universe operate this way? Why would it build such an intricate, invisible connection between particles, then hide it from plain view? Every answer we uncover seems to lead to deeper questions, pulling us further into the enigma. And if entanglement is just one piece of a much larger puzzle, what other hidden rules are waiting to be discovered? The universe, it seems, loves keeping secrets, but each revelation brings us closer to understanding the true fabric of reality. Galaxies spin so fast that their visible stars and gas should fling apart, yet they don't. Something invisible holds them together, an unseen force we call dark matter. Picture a carousel spinning wildly, its horses threatening to fly off, but invisible ropes keep them anchored. That's dark matter's role in the cosmos, a hidden scaffold keeping galaxies intact. The proof isn't just theoretical. Take the Bullet Cluster, two galaxy clusters that collided in one of the most violent cosmic events ever observed. When scientists mapped the aftermath, they found something astonishing. The visible gas slowed and heated up, but the gravitational lensing effect, which reveals mass, didn't follow the gas. Instead, it stayed with something unseen, like a shadow parting from its owner. This was dark matter, drifting through the wreckage unscathed, proving it's not just an idea, it's real and it's out there. But what is it? Some physicists think dark matter could be a yet undiscovered particle, a cosmic ghost that barely interacts with light or matter. Others wonder if we've got gravity all wrong, that instead of invisible matter, we're missing a hidden rule in how gravity behaves on colossal scales. Imagine if the universe's math had a typo, and rewriting it could erase the need for dark matter entirely. Both possibilities are tantalizing, and both force us to question how much we truly understand about the forces shaping reality. And then there's its mysterious counterpart, dark energy. While dark matter pulls galaxies together, dark energy does the opposite, pushing the universe apart at an accelerating rate. It's as if the cosmos is stretching itself thinner and thinner, driven by an invisible pressure we can't explain. Together, these two hidden forces govern the universe's fate, one binding it, the other tearing it away. The irony: over 95% of the universe is made of these enigmas, and we're left staring at the tiny fraction we can actually see. It's humbling, really. The more we uncover, the clearer it becomes that the universe is playing a game we're only beginning to learn the rules of. If dark matter is the universe's invisible glue, dark energy is its phantom push, a force so baffling it makes galaxies flee from one another faster and faster as time goes on. Picture blowing up a balloon with dots on its surface. As the balloon expands, the dots drift apart. But now imagine the balloon starts inflating faster, as if some unseen hand keeps pumping more air into it. That's what dark energy is doing to our cosmos, stretching space itself at an accelerating rate. In 1998, astronomers made the jaw-dropping discovery that the universe wasn't just expanding, it was speeding up, as if repelled by some anti-gravity rule. This revelation was so monumental that it earned the 2011 Nobel Prize in Physics, rewriting our understanding of cosmic fate. Here's the twist: dark energy isn't just some minor player. It makes up a staggering 68% of the universe's total energy and matter, dwarfing everything we can see or touch, and yet we have no idea what it actually is. One leading theory suggests it might be an intrinsic property of space itself, what physicists call vacuum energy. Even in a completely empty void, quantum fluctuations create a seething sea of particles popping in and out of existence. Could this microscopic chaos generate enough pressure to drive the universe apart? The math says it's possible, but there's a catch. When scientists calculate the predicted energy of this quantum foam, the numbers overshoot reality by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, a discrepancy so colossal it's been called the worst theoretical prediction in the history of science. Another possibility: dark energy might not be constant at all. Some models propose it's a dynamic field, evolving over time like an invisible tide, ebbing and flowing through the cosmos. If true, this could mean the universe's acceleration isn't set in stone. It might slow down, speed up further, or even reverse one day. Imagine a cosmic tug of war where the fate of everything hinges on a hidden force we can't yet measure. What's at stake isn't just academic curiosity. If dark energy's push grows stronger, it could eventually tear apart galaxies, then stars, and finally even atoms in a distant future called the Big Rip. Alternatively, if it weakens, gravity might regain dominance, pulling everything back into a fiery collapse. Or perhaps space will keep stretching quietly, leaving galaxies isolated in an ever-darkening void. The unsettling truth: we're deciphering the universe's hidden rules with only fragments of the blueprint, like trying to predict the end of a movie after glimpsing just one scene. Dark energy isn't just a mystery, it's the ultimate wild card in the story of everything. Empty space isn't really empty. At the smallest scales, even a perfect vacuum seethes with activity particles flickering in and out of existence like cosmic static, here one instant and gone the next. These quantum fluctuations aren't just theoretical. In 1948, physicist Hendrik Casimir made a startling prediction. If you place two metal plates incredibly close together in a vacuum, the particles popping into existence outside the plates would exert more pressure than those between them, creating a measurable force that pushes the plates together. 2 decades later, experiments confirmed this exact effect, proving that so-called nothingness is actually a bubbling cauldron of energy. This discovery raises an electrifying question. Could the energy of empty space hold the key to some of the universe's greatest mysteries? Take dark energy, that enigmatic force accelerating cosmic expansion. One leading theory suggests it might be fueled by vacuum energy, the collective buzz of these fleeting particles. But there's a problem. When physicists calculate how much energy these fluctuations should generate, the numbers overshoot observed reality by a mind-boggling margin. It's as if the math predicts a tsunami, but we only see ripples. This cosmological constant problem remains one of physics' most glaring unsolved puzzles, hinting that we're missing a crucial piece of the puzzle, perhaps a hidden rule that tames the vacuum's wild energy into the subtle force we observe. Now imagine harnessing that power. Theoretical warp drives, often relegated to science fiction, rely on manipulating spacetime itself. Some designs propose using negative energy, a speculative state where vacuum energy is twisted into repelling gravity, to compress space ahead of a ship and expand it behind, effectively allowing faster than light travel without breaking Einstein's speed limit. While this remains far beyond our current technology, the fact that such ideas are even debated shows how profoundly quantum vacuum physics could reshape our future. The deeper we look, the stranger it gets. What we call empty might be the most dynamic canvas of all, scribbled with invisible rules that dictate everything from the fate of galaxies to the fabric of spacetime. If even nothingness holds this much power, what other secrets is the universe hiding in plain sight? What if everything you see, the stars, the oceans, even your own hands, isn't truly three-dimensional, but a projection like a cosmic mirage? This is the essence of the holographic principle, one of the most radical ideas in modern physics. It suggests that all the information in our universe might be encoded on a two-dimensional surface at the edge of space, like a hologram where a flat image creates the illusion of depth. The roots of this mind-bending concept trace back to black holes, those enigmatic cosmic traps where gravity is so strong that not even light escapes. In the 1970s, physicist Jacob Bekenstein made a startling discovery: black holes have entropy, a measure of disorder, and it's proportional to their surface area, not their volume. This hinted that all the information swallowed by a black hole isn't lost inside it but smeared across its event horizon, like data etched onto an invisible sphere. String theory takes this further, proposing that the fabric of reality might be woven from tiny, vibrating strings whose interactions create the illusion of a three-dimensional world. Imagine a movie screen. No matter how lifelike the images appear, they're all just patterns of light on a flat surface. If the holographic principle holds, our universe might work the same way, with every particle, every force, every moment in time emerging from a hidden, lower-dimensional code. But why would the universe operate like this? One clue lies in entropy, the tendency of systems to move from order to chaos. If information is the universe's true currency, then entropy becomes a ledger, tracking how that information spreads and transforms. Think of it like a cosmic hard drive. The more disordered a system becomes, the more bits are needed to describe it. The holographic principle suggests there's a limit to how much information any region of space can hold, as if reality has a built-in storage capacity. The implications are staggering. If the universe is a hologram, then free will, consciousness, even the passage of time might be emergent phenomena, illusions arising from deeper, simpler rules. It's a humbling thought. Everything we experience, from the vastness of galaxies to the warmth of sunlight, could be the universe's way of rendering data, like a cosmic virtual reality. And if that's true, what or who is running the simulation? The answer might lie in the next hidden rule waiting to be uncovered. Ever watch an egg shatter on the floor and think, why doesn't it just reassemble itself? The answer lies in one of the universe's most relentless hidden rules, entropy. At its core, entropy is a measure of disorder, and the second law of thermodynamics states it always increases in an isolated system. That's why heat flows from hot to cold, why perfume spreads through a room, and why you'll never see a broken cup spontaneously mend itself. Time, it seems, has a preferred direction, an arrow pointing relentlessly toward chaos. But here's the paradox. At the microscopic level, the laws of physics are perfectly reversible. If you filmed two atoms colliding and played the tape backward, you couldn't tell the difference. Every interaction looks the same in reverse. So why does the macroscopic world refuse to rewind? Imagine a deck of cards neatly ordered by suit and number. Shuffle it once, and it's slightly disordered. Shuffle it 100 times, and the original sequence is lost in a sea of randomness. The individual shuffles are reversible, but the odds of stumbling backward into perfect order are astronomically low. That's entropy in action, a statistical inevitability, not a fundamental law. Chaos theory takes this further, revealing how tiny, unpredictable fluctuations can snowball into irreversible change. A single gust of wind alters the path of a falling leaf. A minute variation in a planet's orbit reshapes its trajectory over millennia. These systems are exquisitely sensitive to initial conditions, making it impossible to perfectly rewind the tape of reality. Even if you could reverse every particle's motion, some quantum flicker or unseen variable would nudge the system onto a new path. What's fascinating is how this connects to time's arrow. Some physicists argue entropy isn't just a byproduct of time, it's the reason time feels like it flows forward at all. In a hypothetical universe where entropy always decreased, you'd remember the future and forget the past, watching shattered glasses leap onto tables and smoke retreat into chimneys. Our brains, themselves products of increasing entropy, might interpret that world as time running backward. So is entropy the hidden clockwork of the cosmos. It's a compelling thought. From the birth of the universe in a low entropy Big Bang to the eventual heat death where all energy dissipates, entropy shapes the story of everything. And yet, pockets of order persist, stars ignite, life emerges, consciousness arises, as if the universe is fighting its own inevitable decay. That tension between chaos and complexity might just be the most profound rule of all. A butterfly flaps its wings in Brazil, and weeks later, a tornado rips through Texas. This isn't poetry, it's chaos theory in action. The startling idea that minuscule changes in initial conditions can snowball into wildly unpredictable outcomes. At first glance, it feels like randomness reigns supreme, but here's the twist: chaotic systems aren't actually random. They're governed by strict deterministic laws, equations that, in theory, should let us predict everything perfectly. Yet in practice, they spiral into apparent disorder, like a clockwork machine that somehow keeps surprising its maker. Take weather prediction, for example. Meteorologists use some of the most advanced supercomputers on Earth, crunching countless variables: temperature, pressure, wind speed, to forecast storms. But even with perfect data, tiny errors compound exponentially. A measurement rounded to the 10th decimal place might seem negligible, yet over days, that microscopic uncertainty grows into completely divergent forecasts. It's why we can't reliably predict weather beyond 2 weeks, despite knowing all the underlying physics. The system isn't broken, it's simply wired to amplify the smallest whispers into roars. Now imagine a double pendulum, a pendulum with another pendulum attached to its end. Swing it gently, and its motion seems orderly. But nudge it just slightly differently, and within seconds, it's whirling in frenzied, unpredictable loops. Despite this chaos, the pendulum isn't defying physics. It's obeying Newton's laws to the letter. The madness emerges from the system's extreme sensitivity, a phenomenon mathematicians call deterministic chaos. It's as if the universe embedded a fail-safe against predictability, ensuring some outcomes always remain just out of reach. But what if chaos isn't the absence of order, but a veil hiding deeper patterns? Enter fractals, infinitely complex shapes that repeat themselves at every scale. Zoom into a jagged coastline or the branching veins of a leaf, and you'll see the same intricate structures recurring endlessly. Even chaotic systems, when mapped over time, often reveal fractal geometries in their behavior. The famous Lorentz attractor, a model of atmospheric convection, traces a butterfly-shaped curve in phase space, a stunning blend of chaos and hidden symmetry. Could these fractal fingerprints be clues to a grander design? Some scientists speculate that beneath the turbulence of chaotic systems lies a hidden architecture, a mathematical scaffolding that turns apparent disorder into an intricate dance. If true, then chaos might not be the universe's way of resisting predictability, but of encoding it in a language we're only beginning to decipher. The more we study these patterns, the clearer it becomes. Even in the wildest storms, there's a method to the madness, and it's written in the geometry of the unseen. Look closely at a tree, and you'll notice something extraordinary. The way its branches split mirrors the way its smaller twigs divide, and those twigs mirror the veins in its leaves. Zoom out, and river systems carve the same branching patterns into continents, while lightning bolts fork across the sky in identical jagged stitches. These aren't coincidences, they're fractals, nature's way of repeating a simple blueprint at every scale, from the microscopic to the cosmic. Mathematician Benoit Mandelbrot first named this phenomenon in the 1970s, revealing that chaos and complexity could emerge from astonishingly simple mathematical rules. His eponymous Mandelbrot set a swirling, infinitely intricate shape generated by iterating a single equation, proved that boundless complexity could arise from pure logic. It's as if the universe has a favorite formula, one it uses to sculpt everything from fern fronds to galaxy clusters. But why would nature rely so heavily on fractals? Efficiency. A fractal structure maximizes surface area while minimizing resource use. Your lungs, for example, pack the surface area of a tennis court into your chest by branching in fractal patterns. Blood vessels do the same, ensuring every cell receives oxygen with minimal energy waste. Even coastlines, when measured with increasing precision, grow longer without ever reaching a final length, a property Mandelbrot called fractal dimension. This isn't just math, it's a hidden engineering principle woven into the fabric of reality, optimizing everything from nutrient distribution in plants to the clustering of matter in the cosmos. The deeper implication, fractals suggest the universe has an innate drive towards self-organization. Take the Fibonacci sequence, where each number is the sum of the two before it. This simple rule generates the golden spiral, a fractal pattern seen in sunflower seeds, hurricanes, and spiral galaxies alike. It's as if nature stumbles upon the same elegant solutions again and again, guided by an invisible mathematical hand. Even the distribution of galaxies across the cosmos isn't random. It follows a fractal-like clustering, with voids and filaments repeating across billions of light years. Could this mean math isn't just a human invention, but the universe's native language? Constants like pi and the golden ratio appear relentlessly in unrelated phenomena, from the orbits of planets to the spirals of seashells. Physicist Max Tegmark goes further, proposing that reality is mathematics, that we're living in a giant mathematical structure, where every law of physics is just another equation waiting to be solved. If true, then fractals might be more than pretty patterns. They could be glimpses into the source code of existence, where simplicity and complexity dance in an endless loop. The question isn't just why nature loves fractals, it's whether the universe itself is one vast, self-repeating equation. Imagine tweaking the universe's settings just slightly, making gravity a fraction stronger or weakening the electromagnetic force by a hair. Suddenly, stars burn out too quickly, atoms can't bond, and life as we know it becomes impossible. This isn't science fiction, it's the startling reality of cosmic fine-tuning. Take the strength of gravity, for example. If it were even 1% stronger, the universe would have collapsed back into itself moments after the Big Bang. 1% weaker, and matter would have scattered too thinly for stars and galaxies to form. The numbers don't just suggest precision, they scream intentionality. The cosmological constant, which governs the expansion of the universe, is calibrated to within 1 part in 10 to the power of 120. That's like hitting a bullseye on a dartboard the size of the observable universe, blindfolded on the first throw. So why does the universe seem tailor-made for life? One explanation is the Anthropic Principle, the idea that we observe these perfect conditions simply because we're here to observe them. If the constants weren't just right, we wouldn't exist to ponder them. It's a cosmic version of survivorship bias, like a puddle marveling at how perfectly its hole fits its shape. But this raises another question. Is our universe the only one? Some theorists propose a multiverse where countless universes bubble into existence, each with different physical laws. In most, conditions are inhospitable, no stars, no planets, no life. But in a rare few, like ours, the dice roll just right. It's a compelling idea, though frustratingly difficult to test. How do you observe a universe where gravity crushes atoms instantly, or where time flows backward? Then there's the simulation hypothesis, the notion that our universe might be an advanced civilization's digital creation. If true, the fine-tuning could simply be lines of code, parameters set by programmers running a cosmic experiment. It sounds like sci-fi, but some physicists take it seriously. After all, if future humans could simulate conscious beings, why wouldn't they? And if simulations outnumber base realities, the odds favor us living in one. But here's the twist: whether the universe is one in a multiverse, a simulation, or something else entirely, the fine-tuning remains. It's a puzzle that forces us to confront the deepest questions. Is there a designer? A cosmic accident, or are we missing an even bigger picture? The constants of nature aren't just numbers, they're clues pointing toward mysteries we've only begun to unravel. What if everything around us, the stars, the oceans, even our own thoughts, isn't real, but an incredibly advanced simulation? Elon Musk famously put the odds at 1,000,000,000 to 1 that we're living in base reality, while philosopher Nick Bostrom laid out a chillingly logical case for why future civilizations might create ancestor simulations so detailed their inhabitants would never know the difference. The argument hinges on 3 possibilities. Either civilizations never reach the technological capability to run such simulations, they choose not to, or we're almost certainly inside one right now. Given the exponential growth of computing power, the first scenario seems unlikely, so where does that leave us? Clues might be hiding in the fabric of reality itself. At the smallest scales, the universe behaves strangely pixelated. Take Planck length, the shortest measurable distance in physics. Below this scale, space and time lose meaning, as if the universe has a built-in resolution limit, like a digital screen where you can't zoom in further without seeing the pixels. Quantum mechanics adds to the mystery. Particles exist in fuzzy, probabilistic states until observed, as if the simulation only renders them when needed to save processing power. Even the speed of light could be a cosmic frame rate, preventing the system from overloading by capping how fast information can travel. But the most unsettling question isn't about physics, it's about consciousness. If we're simulated beings, are our thoughts and emotions just lines of code, or is there something more? Some theorists argue that consciousness itself might be the ultimate glitch, an emergent property too complex for even the most sophisticated programmers to fully control. Others suggest that if a simulation can generate self-aware beings, then by definition, their experiences are as real as anything outside the simulation. After all, pain would still hurt, joy would still uplift, whether the world is made of atoms or algorithms. The simulation hypothesis forces us to confront uncomfortable possibilities. Are the laws of physics just user settings? Could cosmic fine-tuning be a debug mode left active? And if this is a simulation, who or what is running it? Perhaps we'll never know for sure, but the mere possibility reshapes how we see reality, turning the universe into the ultimate puzzle box, waiting to be cracked open. Whether we're in a simulation or not, one thing's certain: the deeper we dig, the stranger the truth becomes. What if consciousness isn't something the brain creates, but something the universe is made of? Panpsychism, one of the most provocative ideas in philosophy and physics, suggests that awareness isn't unique to living beings. It's woven into the fabric of reality itself, from electrons to galaxies. Think of it like this: just as gravity exists everywhere, acting on all matter, consciousness might be a fundamental property of existence, as intrinsic to the cosmos as space and time. At first glance, it sounds like mysticism, but cutting-edge science is starting to flirt with this radical notion. Take the famous double-slit experiment, where particles like electrons behave as waves when unobserved, spreading out in fuzzy probabilities. But the moment a detector is placed to watch them, they snap into definite positions, as if reality itself changes when consciousness enters the picture. This isn't just a quirk of quantum mechanics, it's a seismic hint that observation and existence might be entangled in ways we barely understand. Now, zoom out further. If consciousness shapes reality at the quantum level, could it also determine the structure of the universe? Some interpretations of quantum mechanics, like the von Neumann-Wigner hypothesis, propose that consciousness causes the collapse of probabilistic waves into concrete events. Without an observer, reality remains a haze of possibilities. This leads to a staggering implication: the universe might not fully exist until something perceives it. Picture a tree falling in an empty forest. If no one's there to hear it, does it make a sound? Quantum physics takes this thought experiment to the extreme, suggesting the tree might not even fall in any definite way until observed. But who or what counts as an observer? Is it limited to humans, or could it extend to animals, plants, even particles themselves? Panpsychists argue that consciousness exists on a spectrum, from the rudimentary awareness of a single atom to the complex self-reflection of a human mind. In this view, the universe isn't a cold, mechanical place. It's a vast, interconnected network of experience, where every piece of matter carries some faint spark of subjectivity. It's a perspective that bridges science and spirituality, suggesting that the cosmos isn't just alive, it's awake. Then there's the multiverse connection. If every quantum possibility branches into a parallel universe, as the many worlds interpretation suggests, could consciousness be the thread that selects which reality we experience? Some theories propose that our awareness acts like a filter, tuning us into one timeline while countless others play out unseen. It's as if the universe is a grand symphony, and consciousness is the instrument that picks out a single melody from the noise. The implications are dizzying. If panpsychism is true, then the boundary between mind and matter blurs beyond recognition. Stars might not think like we do, but they could possess some primordial form of awareness, a cosmic hum underlying their nuclear fires. Black holes, often described as the universe's most destructive forces, might also be its most profound observers, warping space-time in ways that eerily resemble neural networks. Even the vacuum of space, seething with quantum fluctuations, could be a kind of silent sentience, a canvas waiting for perception to paint it into being. So where does this leave us? Either we're accidental passengers in a mechanical universe, or we're participants in something far stranger, a cosmos where consciousness isn't just a byproduct, but a foundational rule. The more we learn, the clearer it becomes. Reality might not just be something we observe, it might be something we co-create. And if that's true, then the greatest mystery isn't just how the universe works, it's how deeply we're woven into its hidden design. Every time you make a choice whether to turn left or right, to speak or stay silent, another version of you might be living the opposite path in a parallel universe. This isn't just science fiction, it's the spine-tingling premise of Hugh Everett's many worlds interpretation. In the 1950s, Everett proposed a radical solution to quantum mechanics' strangest puzzle. If particles exist in multiple states until observed, where do those possibilities go when they collapse into one outcome? His answer: they don't collapse at all. Instead, the universe splits, branching endlessly like a cosmic tree, with every possible outcome playing out in its own reality. Picture Schrödinger's infamous cat alive in one universe, dead in another, with both truths equally real. But here's where it gets wilder. This branching isn't limited to quantum dice rolls. Every flicker of probability, from the decay of an atom to the firing of a neuron, could spawn new timelines. Somewhere, dinosaurs never went extinct. Somewhere else, you're a concert pianist. The multiverse isn't just a collection of alternate histories, it's a ceaseless explosion of what-ifs, each with its own physics, its own stars, its own versions of you. The math checks out, but the implications are dizzying. If every possibility happens somewhere, then somewhere, the laws of physics themselves might be unrecognizable. Now imagine these branches aren't random. What if they follow a hidden rule, a cosmic algorithm dictating how realities divide? String theory offers a tantalizing clue. In its framework, our universe might be one brain floating in a higher dimensional space, with other brains hovering nearby, each hosting its own cosmos. Collisions between these brains could trigger new big bangs, while quantum vibrations might tether them together like invisible threads. Some physicists speculate that entanglement, that spooky link between particles, could be a shadow of these deeper connections, a whisper between worlds. The question isn't just whether multiverses exist, but how they're structured. Are they infinite and chaotic, or do they unfold along some unseen fractal pattern? Could there be a meta-law governing the branching itself, a rule we've yet to name? Every answer pulls us deeper into the mystery, revealing a universe far stranger and far more generous than we ever dreamed. One where every choice, every chance, every possible you gets to exist. The only limit, our imagination, and maybe, just maybe, the hidden rules we're still learning to read. Imagine every particle in the universe isn't a point but a tiny, vibrating string, a cosmic guitar, plucked at different frequencies to create everything from electrons to galaxies. This is string theory's bold vision, an attempt to unify all forces of nature under one elegant framework. But there's a catch. For the math to work, these strings don't just wiggle in the 3 dimensions we know. They dance through at least 10, maybe more, hidden dimensions curled up so tightly that even our most powerful microscopes can't see them. It's like watching a telephone wire from miles away. It appears as a one-dimensional line, but up close, it's a thick cable with depth and structure. Our universe might be just as deceiving, its true shape lurking in dimensions we've yet to perceive. So where are these extra dimensions? Picture a Calabi-Yau manifold, a complex, 6-dimensional shape smaller than an atom, twisted into intricate folds like an origami masterpiece. These shapes aren't arbitrary. They're mathematical solutions to how extra dimensions could compactify or curl up without disrupting the physics we observe. Think of them as the universe's hidden origami, each crease influencing how strings vibrate and thus determining the properties of particles. One fold might give rise to electrons, another to quarks, as if the fabric of reality itself is tuned by these invisible geometries. Here's the mind-bending part. What if these higher dimensions aren't just mathematical abstractions, but realms with their own rules we're oblivious to, like shadows on a cave wall mistaking flickers for reality? Plato's ancient allegory feels eerily prescient. A shadow doesn't reveal the object casting it, just as our 3D world might be a crude projection of richer, multidimensional truths. Gravity, for instance, seems oddly weak compared to other forces. Could it be leaking into other dimensions, diluted across membranes we can't access? String theory's promise and its frustration is that it offers a potential theory of everything, while demanding we accept realities we may never directly observe. But perhaps that's the point. The universe has never been content to play by rules we find convenient. From quantum weirdness to dark energy, it delights in hiding its deepest truths just beyond our grasp. The question isn't whether extra dimensions exist, it's whether we're ready to admit how much of reality we've been missing. Black holes aren't just cosmic vacuum cleaners, they're the universe's ultimate shredders, swallowing stars, planets, and even light itself without leaving a trace. But in the 1970s, Stephen Hawking dropped a bombshell. These gravitational monsters might be erasing something far more fundamental than matter. Information, according to quantum mechanics, information, the blueprint of every particle's state, position, and history, can never truly be destroyed. Even if you burn a book, the ashes still contain traces of its pages, just scrambled. But Hawking showed that black holes evaporate over time, emitting faint radiation that carries no details about what fell in. It's as if the universe's hard drive is being wiped clean, violating one of physics' most sacred rules. This paradox sent shockwaves through the scientific community, pitting quantum theory against gravity in a battle that's still raging today. The stakes couldn't be higher. If Hawking was right, our understanding of reality has a glaring hole, literally. But in 2020, the Nobel Prize in Physics was awarded to Roger Penrose, Reinhard Genzel, and Andrea Ghez for proving black holes aren't just theoretical nightmares, they're real, and their behavior could rewrite physics. Penrose's work on singularity theorems showed that black holes are inevitable under Einstein's relativity, while Genzel and Ghez provided ironclad evidence of a supermassive black hole lurking at the Milky Way's heart. Their discoveries didn't solve the information paradox, but they sharpened the question: how can something so real break the universe's most basic rules? Enter the holographic principle. Imagine a black hole's event horizon, the point of no return, as a two-dimensional surface where all incoming information gets smeared like ink on a page. According to this idea, the data isn't lost, it's encoded on the horizon's surface, preserved in a form we don't yet understand. It's like burning that book but finding its contents etched into the smoke. This holographic solution suggests black holes might not be destroying information after all, just transforming it in ways that defy intuition. Some theories even propose that what emerges from a black hole's evaporation isn't random noise, but a scrambled version of everything it consumed, waiting to be decoded. Now take this a step further. If information can escape, could matter, white holes, the hypothetical opposites of black holes, might hold the answer. While black holes suck everything in, white holes spew everything out like cosmic fountains. Some physicists speculate that black holes could tunnel into white holes, turning destruction into creation. Picture a universe where every black hole is a one-way door to somewhere or someone else, recycling matter and energy in an endless loop. It's a wild idea, but it hints at a deeper symmetry in the cosmos where nothing is truly lost, only reborn. The paradox forces us to confront a humbling truth: black holes aren't just objects. They're laboratories testing the limits of our knowledge and daring us to dream bigger. Whether they're holograms, recyclers, or something stranger, one thing's clear: the universe keeps its deepest secrets hidden in the darkest places. And the closer we look, the more we realize how much we've yet to learn. If black holes are the universe's ultimate devourers, then white holes would be its most generous givers, cosmic fountains spewing out matter and energy instead of swallowing them. Picture a black hole in reverse, where gravity's grip is so repulsive that nothing can enter, only escape. The math allows it. Einstein's equations work just as well backward in time, but no one's ever seen one. Could that be because white holes aren't just theoretical oddities, but the hidden counterparts to black holes, playing by a rule we've yet to fully grasp? Some physicists speculate that when a black hole dies, it might not vanish in a puff of radiation but transform into a white hole, rebooting the information it consumed back into the cosmos. It's a tantalizing idea, like the universe has a recycling system where black holes compress matter into oblivion and white holes blast it back out fresh and new. Even more radical is the suggestion that the Big Bang itself could have been a white hole event, a primordial eruption of space and time from some other universe's collapsed singularity. Imagine our entire cosmos as the exhale of a cosmic lung, with black holes elsewhere inhaling matter into another reality entirely. This isn't just wild speculation. Cyclic universe models, like Roger Penrose's conformal cyclic cosmology, propose that the far future of one universe could seed the Big Bang of the next, with black holes playing a key role in the transition. In this view, time isn't linear but circular, an endless loop of contraction and expansion governed by hidden symmetries. The eerie smoothness of the cosmic microwave background, the afterglow of the Big Bang, might even carry faint imprints of black holes from a previous eon, like echoes of a universe that came before. But here's the real mystery. If white holes exist, where are they? One possibility is that they're fleeting, appearing only for an instant before collapsing or evaporating. Or perhaps they're disguised as something else. Gamma-ray bursts, those incomprehensibly violent explosions in deep space, could be white holes announcing their birth. There's even a fringe theory that dark matter, the invisible glue holding galaxies together, might be composed of microscopic white holes sprinkling the cosmos with unseen mass. The deeper we dig, the clearer it becomes. Black holes and white holes might not be opposites, but two sides of the same cosmic coin. A hidden rule of respiration, inhale and exhale, collapse and rebirth, could be woven into the fabric of space-time itself. Whether this cycle spans universes or unfolds within our own, one thing's certain: the universe has a knack for turning endings into beginnings and death into something far stranger. The Big Bang is often called the birth of our universe, but what if it was more like a cosmic reboot? Loop quantum gravity, a leading theory attempting to bridge Einstein's relativity with quantum mechanics, suggests something extraordinary: that the Big Bang wasn't a true beginning, but the aftermath of a previous universe's collapse. Imagine a cosmic bounce, an ancient universe contracting under gravity until it reached a point of infinite density, then rebounding outward in the explosion we now call the Big Bang. It's as if reality has a reset button, cycling through expansion and collapse like a celestial heartbeat. The math behind this big bounce is elegant, replacing the singularity, a point of infinite curvature where physics breaks down, with a quantum bridge linking one epoch of existence to the next. Yet this raises another puzzle. Why does our universe look so uniform? The cosmic microwave background, the oldest light we can observe, paints a picture of startling consistency across the sky. No matter which direction we look, the temperature varies by less than 1 part in 100,000, a smoothness that defies expectation. If the universe began in a violent explosion, why isn't it lumpy, with pockets of extreme heat and cold? One explanation is cosmic inflation, a theoretical burst of exponential expansion in the universe's first fraction of a second. But inflation itself demands explanation. What triggered it? Could it be a relic of that pre-Big Bang universe, a hidden rule carried over from the previous cycle? Then there's the enigma of dark flow. Clusters of galaxies billions of light years away seem to be drifting in the same direction, as if tugged by something beyond the observable universe. This motion can't be explained by known forces. It's as if the ghosts of a prior cosmos are still influencing ours. Some theorists speculate that these galaxies are caught in the gravitational wake of a sister universe, one that branched off from our own during the Big Bang or even before it. Picture a vast cosmic ocean with our universe just one current among many, all flowing from some deeper, unseen source. The deeper we probe, the clearer it becomes. The Big Bang might not have been the ultimate beginning, but a transition, a moment when the rules of reality reshuffled, leaving echoes of what came before. Whether it was a bounce, a collision of higher dimensional brains, or something beyond our current imagination, the answer lies in the cracks between our theories. And if we're right, the universe's greatest secret isn't how it began, but what it remembers. Galaxies aren't just drifting apart as the universe expands. Some are being pulled en masse towards something we can't see. This eerie motion, dubbed dark flow, was first detected in 2008 when astronomers noticed hundreds of galaxy clusters streaming in the same direction at staggering speeds, over 2 million miles per hour. It's as if an invisible hand is tugging them toward a point beyond the edge of our observable universe, a cosmic attractor so vast it defies explanation. The strangest part, this motion shouldn't exist. The Big Bang's afterglow, the cosmic microwave background, paints a universe that's remarkably uniform in all directions. There's no obvious imbalance in gravity or energy to account for such a coherent, large-scale drift. So what's pulling these galaxies? One possibility is that dark flow is a glimpse of something beyond our cosmic horizon, a supermassive structure lurking in the unobservable reaches of space. Imagine standing in a valley, unable to see the mountain just beyond the mist, but feeling its gravitational pull in the way trees lean and rivers bend. If such a structure exists, it would have to be incomprehensibly massive, perhaps a cluster of galaxies 100 times larger than anything we've seen, or even the gravitational wake of another universe brushing against ours. This idea ties into the multiverse hypothesis, where our cosmos is just one bubble in an infinite foam of universes, each with its own physics. The dark flow could be the first evidence that we're not alone in the greater multiverse, that something vast and foreign is close enough to tug at our celestial fabric. But there's a catch. Dark flow might not be real at all. Some scientists argue it's an artifact of incomplete data or measurement errors. Others propose a radical alternative, that our understanding of gravity itself is flawed. Modified Newtonian dynamics, or MUND, suggests gravity behaves differently on cosmic scales than Einstein's relativity predicts. If true, dark flow could be a phantom, a trick of gravity's hidden rules playing out in ways we don't yet comprehend. The debate forces us to confront a deeper question. What shape is the universe? Is it flat like an infinite sheet or curved like the surface of a globe? Or could it be something far stranger, a twisting fractal geometry that changes depending on where you look? The answer lies in the cosmic microwave background's subtle wrinkles, patterns that might reveal whether space stretches forever or loops back on itself. If the universe is finite, dark flow could be evidence of its edges, a cosmic current circling a hidden drain. If it's infinite, the mystery only deepens, pointing to forces or realms beyond our wildest imagination. Either way, one thing's clear: the universe isn't just expanding, it's moving, pulled by secrets we've only begun to sense. The shape of the universe isn't just a curiosity, it's a cosmic blueprint, dictating everything from the fate of galaxies to the very nature of reality itself. Picture space as a colossal sheet of paper. If it's perfectly flat, parallel lines will never meet, and the universe will expand forever, thinning into cold emptiness. But if it's curved like a sphere, those lines will eventually converge, pulling the cosmos back into a fiery collapse. Then there's the third option, a saddle shape, where space curves outward in opposite directions, dooming the universe to expand at an ever-accelerating rate, tearing itself apart. The Planck Space Telescope, measuring the cosmic microwave background with unprecedented precision, delivered a bombshell. The universe appears almost exactly flat, with a margin of error so tiny it's like measuring the smoothness of a marble the size of Earth. But here's the catch: flatness on observable scales doesn't rule out wilder possibilities. Topology, the study of shapes and their properties, suggests the universe could be flat but still finite, like a video game world where traveling far enough in one direction brings you back to where you started. Imagine an ant crawling on a donut. Its surface is locally flat, but globally, it's a twisted loop. If our cosmos has hidden folds or tunnels, wormholes stitching distant regions together, light might have taken shortcuts, creating ghostly duplicates of galaxies or eerily repeating patterns in the cosmic microwave background. Some theorists even propose the universe could be a dodecahedron, a 12-sided die where each face mirrors another, weaving space into a hall of mirrors on a scale beyond comprehension. The real mystery isn't just what shape the universe is, but why it's shaped that way. Inflation, the universe's explosive growth spurt in its first moments, likely ironed out any primordial curvature, leaving us with this eerie flatness. But was this a chance outcome, or does it hint at a deeper rule, a cosmic preference for stability, or even a selection effect? If multiple universes bubble into existence with random geometries, perhaps only the flat ones last long enough to host galaxies, planets, and life. Then there's dark energy's role. If the universe is flat yet expanding faster and faster, could its geometry be dynamic, warping over eons? Some models suggest that dark energy might not be constant but evolving, subtly bending space in ways we can't yet detect. It's as if the universe is a living sculpture, its shape shifting under invisible hands. The stakes couldn't be higher. A closed universe might one day reverse its expansion, collapsing into a big crunch. An open one could dissolve into absolute zero, but if it's truly flat, the end might be stranger, a slow fade into darkness where galaxies vanish beyond an unreachable horizon. Yet hidden in that flatness could be clues to realities beyond our own, folded dimensions or gateways to other times and places. The universe's shape isn't just a question of geometry, it's a riddle about the rules written into the fabric of existence, waiting to be decoded. Einstein's equations didn't just predict black holes, they hinted at something even stranger. Wormholes, cosmic tunnels stitching distant corners of spacetime together like hidden seams in the fabric of reality. Picture folding a piece of paper so 2 points touch, then piercing through with a pencil. That's the essence of an Einstein-Rosen bridge, a shortcut through the universe's crumpled geometry. These theoretical passages emerge straight from the math of general relativity. But here's the catch: they're catastrophically unstable. Without some exotic ingredient holding them open, they'd snap shut faster than light could traverse them, crushing anything inside. That's when negative energy enters the equation, a hypothetical substance with repulsive gravity, pushing spacetime apart instead of pulling it together. Think of it like cosmic duct tape, propping the wormhole's throat open just long enough for a traveler to slip through. Quantum mechanics offers a glimmer of hope here. The Casimir effect, where empty space crackles with fleeting particles, can generate tiny amounts of negative energy between closely spaced plates. Scale that up to astronomical proportions, and you might stabilize a wormhole, but the numbers are daunting. The energy required could exceed the total output of a star, and the engineering challenges border on magic. Yet the tantalizing possibility remains. What if the universe has hidden rules that make faster-than-light travel possible without violating causality? Some models suggest wormholes could function as time machines, with one end aging slower than the other due to relativistic effects. Step in, and you might emerge not just across the galaxy, but centuries in the past or future. The catch paradoxes loom. If you travel back and prevent your own journey, did the trip ever happen? Physics abhors such loops, leading many theorists to conjecture that quantum effects or unknown laws would inevitably collapse the wormhole the moment a paradox threatened. But imagine a universe where wormholes are natural features, woven into spacetime's architecture like subway tunnels through a city. Ancient cosmic civilizations might have mapped them, using them as interstellar highways long before our species even looked up at the stars. Or perhaps they're microscopic, flickering in and out of existence at the quantum level, connecting every point in space in a frothing network we're too large to perceive. The math doesn't rule it out, it just asks us to dream bigger. The real question isn't whether wormholes exist, but whether the universe allows them to be more than mathematical curiosities. If they do, the implications rewrite the rules of exploration, turning the cosmos into a neighborhood instead of an endless frontier. And if they don't, well, the universe has surprised us before. Every hidden rule we've uncovered started as an impossible idea until it wasn't. Time crystals sound like something ripped from science fiction, but they're very real, and they defy one of the most fundamental laws of physics. Unlike everything else in the universe, these bizarre structures don't settle into equilibrium. Instead, they pulse, oscillate, and repeat their patterns indefinitely without any energy input, like a clock that ticks forever without winding. The idea was first proposed by Nobel laureate Frank Wilczek in 2012, and by 2017, scientists had brought them to life in labs using chains of ions or diamond defects chilled to near absolute zero. The key, these crystals don't just repeat in space. Like the atomic lattices of regular crystals, they repeat in time, locking into rhythms that resist entropy's relentless pull. What makes this so revolutionary is that it skirts the edge of perpetual motion, a concept long dismissed as impossible. Thermodynamics insists that energy always dissipates, that disorder always grows. Yet time crystals exist in a loophole. Their motion isn't powered by energy, but by a quantum quirk called many-body localization. Picture a row of pendulums that, instead of slowing down, keep swinging in perfect sync, not because they're pushing each other, but because their quantum states are entangled in a dance that never decays. It's as if the universe carved out a hidden exception to its own rules, a pocket where time itself crystallizes into order. This discovery hints at something even wilder, entirely new phases of matter. We're familiar with solids, liquids, and gases, but time crystals suggest there are states beyond these, governed by timeless, self-reinforcing patterns. Some theorists speculate they could be the first examples of non-equilibrium matter, materials that never settle into the calm, disordered haze the rest of the universe succumbs to. If that's true, then the laws we've taken as gospel might just be the tip of the iceberg, with whole realms of physics operating outside time's usual flow. Now tie this to quantum immortality, the idea that consciousness might persist in branching timelines where death is avoided. If time crystals can exist in perpetual cycles, could the universe itself have similar resilient structures, patterns that persist across multiple realities? It's a stretch, but the parallels are eerie. Both concepts flirt with the idea of existence resisting decay, whether through quantum repetition or cosmic redundancy. The deeper we probe, the more it seems the universe has a knack for preserving itself, and perhaps, in ways we're only beginning to glimpse, preserving us too. What if death isn't the end but a doorway? Quantum immortality, one of the most unsettling thought experiments in physics, suggests that your consciousness might never experience death at all. Here's how it works. In the many worlds interpretation of quantum mechanics, every possible outcome branches into a new universe. Now, imagine a scenario where you're subjected to a lethal quantum event, say, a gun triggered by the spin of an electron. In one universe, the gun fires, in another, it doesn't. If consciousness follows the path where you survive, you'd never experience the timelines where you die. It's not that you're invincible, it's that from your perspective, you always land in the reality where you're still alive, no matter how improbable the odds. This idea, sometimes called quantum suicide, was first proposed by physicist Max Tegmark as a grim way to test the many worlds theory. The logic is chilling. If the multiverse exists, the observer you would only ever perceive the branches where you continue to exist, even if those branches become astronomically rare. Picture flipping a coin 100 times and getting heads every single time. Statistically, it's nearly impossible unless you're only aware of the one universe where it happened. But here's where it gets even stranger. What if this isn't just about survival, but a hidden rule of the universe? Some interpretations of quantum mechanics suggest that consciousness itself might play a role in shaping reality, a notion called the participatory universe. If that's true, then the act of observation could be steering us toward timelines where we persist, as if the cosmos has a built-in bias toward continuity. This loops into retrocausality, the idea that future events can influence the past. If your consciousness is somehow entangled with its own future survival, could it be reaching backward, nudging quantum probabilities in your favor? The implications are dizzying. If quantum immortality holds, then every near-death experience, every brush with disaster, might not be luck but evidence of a deeper mechanism, a cosmic safeguard woven into the fabric of reality. Of course, this raises uncomfortable questions. Where are the dead versions of us? Do they simply cease to exist from our perspective? Or is there some deeper interplay between consciousness and the multiverse? Skeptics argue this is little more than solipsism dressed up in quantum jargon, that privileging one's own consciousness as the sole constant across infinite realities is more philosophy than physics. Yet the thought experiment lingers because it forces us to confront the unnerving possibility that reality might not be as objective as we think. Whether it's a quirk of quantum mechanics or a profound hidden rule, one thing's clear: the universe might have a way of keeping us in the game far longer than we ever imagined. What if the future isn't just shaped by the past but shapes it right back? Retrocausality, the mind-bending idea that effects can precede their causes, isn't just a thought experiment. It's a phenomenon that quantum mechanics flirts with every day. Take the infamous delayed choice quantum eraser experiment, where a particle's behavior changes based on a measurement made after it's already been detected. Picture firing photons through a double-slit apparatus. They create an interference pattern, behaving like waves. But if you later erase information about which slit they passed through, the interference magically reappears, as if the particles retroactively decide whether they were waves or particles based on what you eventually choose to measure. It's as though time's arrow isn't just one-directional, but a two-way street where the future whispers back to the past. Now, zoom out further. Could this bizarre behavior hint at a deeper layer of reality? Some theories suggest the zero-point field, the quantum vacuum teeming with fleeting particles, might be the stage where these temporal loops play out. This isn't empty space. It's a seething ocean of energy where particles pop in and out of existence, borrowing energy from the future to pay it back in the past. Imagine throwing a stone into a pond, but the ripples reach backward, altering the moment the stone was thrown. That's the kind of causality flipping dance the quantum world seems to tolerate, if not outright encourage. The implications are staggering. If retrocausality is real, then free will becomes a tangled knot. Are our choices truly ours, or are they subtly nudged by futures we haven't yet lived? Some interpretations, like the transactional model of quantum mechanics, propose that particles exchange handshakes across time, with waves moving both forward and backward to settle on a single, consistent reality. It's as if the universe is a grand negotiation between past and future, with every moment a compromise between what was and what will be. Here's the real kicker. What if this isn't just a quantum quirk, but a hidden rule of the cosmos? Ancient philosophies spoke of time as cyclical, and modern physics might be catching up. From time symmetric equations to experiments where observers seem to influence events that already happened, the line between cause and effect blurs. Maybe the universe doesn't care which way time flows. It just cares that everything balances in the end. And if that's true, then the past isn't set in stone. It's a story still being written, with the future holding the pen. Even in the deepest vacuum, where every atom and particle has been stripped away, the universe still crackles with energy. This is the zero-point field, a seething ocean of quantum fluctuations where particles flicker in and out of existence so fast they barely leave a trace. The concept sounds impossible, but the proof is etched into reality itself. In 1948, physicist Hendrik Casimir predicted something extraordinary. Place two uncharged metal plates incredibly close together in a vacuum, and they'd be pushed toward each other by an invisible force. The reason, outside the plates, quantum fluctuations can occur at any wavelength, but between them, only certain wavelengths fit. This imbalance creates a pressure differential, proof that empty space isn't empty at all. When scientists finally measured this Casimir effect decades later, it wasn't just a triumph for quantum theory, it was a revelation. The vacuum of space, it turns out, is alive with energy, bubbling beneath the surface of everything we see. Now imagine tapping into that energy. The zero-point field isn't just a curiosity, it's a potential power source beyond anything we've ever harnessed. Theoretical warp drives, the stuff of science fiction, rely on manipulating this vacuum energy to bend spacetime itself. Picture a starship compressing space ahead of it and expanding it behind, riding a wave of distorted reality without breaking the speed of light. The energy required would be staggering, but the zero-point field might hold the key. Some estimates suggest that a single cubic centimeter of pure vacuum contains enough energy to boil all the oceans on Earth. The problem, we'd need to extract it without destabilizing spacetime itself, a challenge that makes nuclear fusion look simple. But here's the deeper mystery. What if this zero-point energy isn't just a quirk of quantum mechanics, but the universe's baseline rule? Some theories propose that dark energy, the force accelerating cosmic expansion, could be fueled by the zero-point field's relentless hum. Yet there's a glaring contradiction. When physicists calculate how much energy the vacuum should contain based on quantum theory, the numbers overshoot observed reality by a factor of 10 to the power of 120. That's like predicting a candle's glow and getting the brightness of 1 trillion suns instead. This cosmological constant problem is one of physics' greatest unsolved puzzles, hinting that we're missing a hidden law that tames the vacuum's chaos into the subtle force we observe. This leads to an even wilder idea. What if the zero-point field isn't just energy, but the fabric of perception itself? Biocentrism, a controversial but fascinating theory, suggests that consciousness isn't a byproduct of the universe, it's the foundation. In this view, the quantum fluctuations of the zero-point field might not exist independently but are shaped by observation, like static resolving into a clear signal when a mind tunes in. It's a radical twist on the participatory universe idea, where reality isn't just out there waiting to be discovered, but co-created through interaction. The zero-point field, then, might be less like a power plant and more like a canvas, its infinite potential waiting to be defined by the act of looking. So is the vacuum's energy the universe's untapped battery, or something far stranger, a mirror reflecting the role of consciousness in shaping reality? The answer might lie in the spaces between our theories, where physics and philosophy blur. One thing's certain, the universe's silence is an illusion. Beneath the apparent stillness, it hums with a force that could rewrite the future, or reveal that the future was never separate from us at all. What if the universe doesn't just exist, but responds? Biocentrism flips the script on everything we think we know about reality, suggesting that life isn't a happy accident in a cold, indifferent cosmos, but the very engine shaping it. At the heart of this radical idea is a simple but staggering premise. Consciousness doesn't emerge from the universe emerges from consciousness. Think of it like a cosmic version of the tree falling in the forest. If no one's there to observe it, does it even happen? Quantum mechanics already hints at this with the observer effect, where particles behave differently when measured, as if aware they're being watched. But biocentrism takes it further, proposing that reality is a participatory phenomenon, a dance between observer and observed where neither can exist without the other. Consider the double-slit experiment, one of quantum physics' most baffling puzzles. When particles like electrons aren't observed, they act as waves, spreading out in a haze of possibilities. But the moment a detector is placed to observe them, they snap into definite positions, as if choosing a state based on our attention. It's not just that measurement changes the outcome, it's that the outcome requires measurement to exist at all. Biocentrism argues this isn't a quirk of tiny particles, but a fundamental rule of the cosmos. Without a mind to perceive it, reality remains a fog of potential, a script waiting for an actor to bring it to life. This leads us to the Mandela Effect, those eerie collective false memories where swaths of people misremember details, like Nelson Mandela dying in prison he didn't, or the Monopoly man wearing a monocle he never did. Skeptics chalk it up to faulty memory, but biocentrism offers a wilder explanation. What if these discrepancies are glitches in consensus reality? If consciousness shapes the world, then shifts in collective perception could subtly rewrite the past, leaving traces of alternate timelines in their wake. It's as if the universe is a collaborative story, and sometimes the editors disagree. The implications are dizzying. If biocentrism holds, then time and space aren't fixed stages but malleable constructs, bending to the presence of life. The Big Bang wasn't the beginning. It was the moment consciousness began observing, collapsing infinite possibilities into the universe we know. Even death might be an illusion, with perception merely shifting to another frame of reality. Critics dismiss this as philosophy masquerading as physics, but the math of quantum mechanics refuses to ignore the observer's role. Whether it's a profound truth or a provocative thought experiment, one thing's clear: the universe might not just have rules, it might be the rules written in the language of life itself. Remember the children's book series about a family of bears? You might swear it was spelled Berenstein, but look closer, it's always been Berenstain. This isn't just a typo. Thousands of people share the same vivid but incorrect memory. a phenomenon so widespread it's been dubbed the Mandela Effect, named after the false collective recollection of Nelson Mandela dying in prison decades before his actual passing. These aren't isolated mistakes. From movie quotes like, "Luke, I am your father," which was never said that way in Star Wars, to the Monopoly man's missing monocle, these discrepancies reveal something unsettling. Memory might not be the reliable record we assume. But what if it's not just faulty recall? What if these glitches hint at something far stranger, hidden rules governing reality itself? One theory points to parallel universes colliding. If the multiverse exists with infinite versions of history playing out in alternate timelines, could fragments of those realities bleed into ours? Imagine two rivers merging. Their waters don't instantly homogenize but swirl together in chaotic eddies. In this model, the Berenstain memory might be a ripple from a nearby universe where the name truly was spelled that way, and our collective consciousness briefly tapped into that timeline. Quantum physics already suggests particles can exist in multiple states until observed. Why not entire events? The catch: there's no way to prove these crossovers, leaving the idea suspended between sci-fi and speculative science. Then there's the simulation hypothesis. If our universe is a digital construct, these inconsistencies could be artifacts of updates or patches, like a video game adjusting its code. Think of The Matrix, where déjà vu was explained as the system altering details midstream. In this view, the Mandela Effect might be the cosmic equivalent of a software glitch, residue from an older version of reality that wasn't fully overwritten. Skeptics argue this is an unfalsifiable claim, but proponents counter that the precision of these shared false memories defies coincidence. Why do so many misremember the same exact details, down to the letter? But perhaps the most haunting explanation lies in the nature of memory itself. Neuroscience reveals that recalling an event isn't like replaying a recording. It's more like reconstructing a puzzle each time, with pieces subtly reshaped by context, suggestion, and time. Every time you remember something, you're not retrieving the original memory but the last version you recalled, creating a game of telephone with your own mind. Social reinforcement amplifies this. When a false detail spreads, it overwrites individual memories, creating a viral inaccuracy. Yet this doesn't fully explain why these specific memories, like the fruit of the Loom logo's non-existent cornucopia, are so universally shared. The Mandela Effect forces us to confront an uncomfortable truth. Reality might be far more malleable than we think. Whether it's quantum echoes, simulation tweaks, or the brain's fragile wiring, these glitches reveal the seams in our perception. They're not just mistakes, they're invitations to question everything we assume is fixed. After all, if memory can't be trusted, what else might be hiding in plain sight? Ever had a moment where you think of someone you haven't spoken to in years, only for them to call you minutes later? Or maybe you dream of an event that later unfolds exactly as you saw it. These aren't just flukes. Psychiatrist Carl Jung called them synchronicities, seemingly random events connected not by cause and effect, but by meaning. Imagine flipping through a book and landing on a passage that eerily answers a question you've been wrestling with. No logical thread ties your action to the message, yet the timing feels too perfect to dismiss as chance. Jung believed these moments reveal a hidden layer of reality where the universe communicates through symbolism, weaving patterns that defy conventional explanation. Take the case of author Arthur Koestler, who once wrote about a man dreaming of a goldfish in a bowl, only to wake and find his child had bought one that very morning. No causality, no rational link, just a startling resonance between inner and outer worlds. Or consider the countless stories of people dodging disasters because they had a feeling to take a different route, skip a flight, or delay their day. These aren't just lucky breaks, they feel like nudges from something larger, as if reality has a way of aligning events to send us a message. But here's the twist. Could these synchronicities point to a deeper rule of the universe, one where meaning operates outside time and space? Quantum entanglement shows particles instantaneously influencing each other across vast distances, as if space is an illusion. If matter can defy classical physics, why not meaning? Some theorists suggest that synchronicities are glimpses of a holographic universe, where every part reflects the whole, and separateness is just a trick of perception. In this view, thinking of a song before it plays isn't coincidence, it's the universe revealing its interconnected fabric. Now, shift to numerology, the ancient belief that numbers carry vibrational significance beyond their mathematical value. Jung saw numbers as archetypes, primal symbols embedded in the collective unconscious. Ever noticed how certain numbers like 1111 appear repeatedly in your life? Skeptics call it pattern seeking, but what if it's the opposite? What if the universe is imposing these patterns, using numbers as a silent language? The golden ratio, for instance, appears in everything from galaxies to seashells, a mathematical constant echoing through nature. Could our personal number synchronicities be miniature versions of this cosmic code? The deeper you dig, the clearer it becomes. Synchronicities challenge the boundary between mind and matter. They suggest a universe that doesn't just operate on physical laws, but on symbolic ones, where a chance encounter, a recurring dream, or a string of numbers might be more than meets the eye. Whether it's Jung's collective unconscious, quantum interconnectedness, or something beyond our current understanding, one thing's certain: reality seems to whisper to those willing to listen. And sometimes those whispers arrive in ways that feel anything but random. Numbers surround us not just as tools for counting, but as hidden signatures woven into the fabric of reality itself. Take the golden ratio, approximately 1.618, a number that appears with uncanny frequency in nature's most exquisite designs. Sunflower seeds spiral in patterns adhering to this ratio, hurricanes coil their arms around it, and even the proportions of your own DNA, the double helix's turns, align with its precise mathematical harmony. Artists like Leonardo da Vinci and architects of the Parthenon embedded this ratio into their masterpieces, sensing an invisible order that resonated with human perception. But here's the mystery: is this number beautiful because we're conditioned to recognize it, or does it tap into a deeper, universal code? Then there's pi, the endless string of digits defining the relationship between a circle's circumference and its diameter. Pi doesn't just govern geometry, it emerges in unlikely places, from the meandering paths of rivers to the oscillations of pendulums, and even the distribution of prime numbers. Its ubiquity raises a provocative question. Are these constants human discoveries, or are they the universe's native language waiting to be decoded? Ancient civilizations like the Babylonians and Egyptians revered these numbers as sacred, while modern physicists treat them as foundational to equations describing black holes and quantum fields. The line between mathematics and mysticism blurs when the same digits appear in galaxy clusters and seashells alike. This duality sparks fierce debate. Some argue numbers are purely human inventions, abstract tools we project onto chaos to make sense of it. But others, like physicist Max Tegmark, propose a radical alternative. That math isn't just a language describing reality, it is reality. In his mathematical universe hypothesis, the cosmos isn't built from matter or energy, but from mathematical structures. Under this lens, the golden ratio isn't just a pattern, it's a cosmic commandment, a rule as fundamental as gravity. Consider the Fibonacci sequence, where each number is the sum of the two before it. This simple rule generates spirals seen in pine cones, galaxies, and even the stock market's chaotic fluctuations. When unrelated phenomena, biology, astronomy, economics, all bow to the same numerical logic, it's hard to dismiss coincidence. Perhaps these aren't accidents, but clues to a grand design, a hidden syntax structuring existence from the microscopic to the cosmic. The implications are staggering. If math is the universe's operating system, then every breakthrough, from quantum mechanics to relativity, isn't just progress, but an act of translation. We're not inventing equations, we're deciphering them, peeling back layers of a pre-written code. This shifts math from a human tool to the ultimate hidden rule, the scaffolding behind everything from the symmetry of snowflakes to the orbits of planets. So are numbers the universe whispering its secrets, or are we hearing echoes of our own minds? The answer might lie in the pattern itself, the way a single equation can describe light's path through a prism and the curve of a spider's web. Whether invented or unearthed, numbers remain the most universal language we've found, bridging the gap between the tangible and the transcendent. And if they truly are the cosmos's hidden rulebook, then every digit is a key, waiting to unlock the next mystery. From the spooky entanglement of particles to the holographic whispers of black holes, every cosmic mystery we've explored points to the same electrifying truth. Our universe operates by hidden rules, laws so profound they're written in a language we're just beginning to decipher. Think about it, quantum particles defying space and time, dark energy stretching the cosmos like an invisible hand, even the eerie synchronicities that feel like the universe winking at us. These aren't just oddities. They're clues, breadcrumbs leading us toward a grander understanding of reality itself. Consider how far we've come by questioning the unseen. A century ago, Einstein's relativity shattered Newton's clockwork universe, revealing that time and space bend like rubber. Decades later, quantum mechanics turned certainty into probability, showing particles exist as waves of possibility until observed. Each breakthrough began with a simple act, refusing to accept the surface explanation. When we dared to ask why galaxies spin too fast or why empty space crackles with energy, we uncovered dark matter and quantum foam, proof that the universe's rulebook is thicker than we ever imagined. This journey isn't just about scientific discovery, it's about human potential. Every mystery solved opens 10 new doors, each more bewildering than the last. The holographic principle suggests reality might be a projection. The multiverse theory hints we're one thread in an infinite tapestry. Even time, that relentless arrow, might be an illusion woven from entropy and observation. These ideas don't just challenge physics, they redefine what it means to exist. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." That's the heart of exploration, not just finding answers, but embracing the questions that keep us up at night. Maybe you'll be the one to crack the next cosmic code, to spot the pattern in the chaos, or hear the universe's hidden melody. The greatest discoveries start with curiosity, with the courage to say, "What if?" So keep wondering, keep questioning, and if today's mysteries left you buzzing with theories, share them below. Let's unravel the universe's secrets together. Don't forget to subscribe. Who knows what we'll uncover next, because the most thrilling rule of all might be this: the deeper we dig, the stranger and more beautiful reality becomes. And the adventure is just beginning.